Hi, I'm Professor Goins. In this video, I'm going to talk about inflection points, which is something that you will learn about in your Calculus 1 course. Okay, first and foremost, recall the concept of concavity. And what I'm going to do is I'm going to start with two functions that are increasing. These could equally as well be decreasing functions, but just to so I don't have to go through both possible cases and the board spaces, at a premium here, I'm going to do just the increasing version. Okay. F is an increasing function, G is an increasing function. We can see that going left to right, the Y values are getting bigger. Okay, so F is increasing, G is increasing. One way to determine that without a graph is to look at the derivative, and if the derivative is positive, we know again that it's an increasing function. But what I want to be able to do is I want to be able to distinguish between these types of increasing without looking at the graph of them, because maybe my function is a little bit too complicated, or maybe I just don't have access to a calculator in these modern days, right? Of course, we all have calculators. You probably have one in your pocket right now on your phone. But at any rate, I want to be able to distinguish between those mathematically, not graphically. So here's how I do this. See how this function is, again, the derivative is positive, but let's take a look at some tangent lines. So let's say that's point of tangency, and then I'm just going to do the right part of the tangent line, just because my graph will get a little bit messed up here. Then these will overlap, so I just want to be able to distinguish between those. So I'll just do two sort of tangent line segments. Now I could do two tangent line segments over here. Once again, all four of those tangent lines have a positive slope, which means the function is increasing. We already know that. But let's now see how these differ. What's different about these? Well, let's put some numbers on this. Okay, so you know that at about 45 degrees, that'd be a slope of 1. This is less than 45, so this is maybe, let's call that a slope of a half. This looks like it's probably a little bit bigger than 45 degrees, so that'd be bigger than 1. Let's call this like 1.4. In other words, maybe a half to 1.4. So the slopes are increasing. Okay, going from this one to this one. You can see that if I draw any more tangent lines on here, these slopes are getting steeper and steeper. So the tangent lines are getting bigger and bigger slopes. Whereas here, again, they're all positive, but let's say this one is at 45 degrees. So this has a slope of 1. Well, this one here is not quite at 45, or it's definitely less than 45. So let's say this is a slope of a half. So I go from 1 to a half. That means that even though they're all positive, here the slopes are decreasing. So the idea is that if the derivatives are positive, in this case here, we can see that the function f prime is increasing. And over here, the slopes are all positive, but they're getting smaller, so therefore the function f prime, the derivative, the values of the derivative are decreasing. Okay? And how do I determine if a function is increasing? Its derivative is positive. Well, if f prime is increasing, then that means that its derivative, which would be f double prime, is positive. Over here, I know that f prime is decreasing. Well, how do I know if a function, just a generic, any function is, I wrote f here. I'm sure some of you are watching saying, that should have been a g. Yes, I'm with you. I got it. Okay, so if the derivative is positive, that means the function let's see. Oh, sorry, I don't have that listed up here. If a function is decreasing, that means its derivative is negative. So that means that g double prime is negative. And terminology-wise, we call this one over here concave up. And this one over here is concave down. So we distinguish concavity with a second derivative. So now let's take a look at this graph right here. Okay, it's got a hill and a valley to it, and there might be some more stuff going on, but this right here is what I want to highlight. If I take a look at, say, this portion right here, so let's just kind of highlight the top of the hill, I can see that this is going to be concave down. And around here at the bottom of the valley there, just again for some informal terminology, this would be concave up. Well, if this is concave down and this is concave up, and the graph is continuous, At some point along here, it's going to have to switch. So we switch from concave up to concave down, or vice versa. And again, we can pretty accurately determine that by just kind of saying, okay, well, this is concave down, this is concave up. Let's kind of trace along the graph here. And certainly here, it still looks like it's concave down. This looks like it's concave up. So it looks like somewhere right around in here, it switches. So let me go ahead and label the left side of that point is concave down, and the right side of that point is concave up. So that means that there's a point in the middle that switches, and that point is referred to as an inflection point. Okay, so this is an inflection point. So conceptually, that's what it is. It's a point on a graph where the concavity differs on either side. Okay, so that's what it is conceptually. Now let's see, how can we determine how to find those mathematically? Okay, so let's take a look at a variety of examples. Actually, let me give you the official definition first. Then we'll go back and we will look at examples. An inflection point is a point on a graph typically I'll just list the x values. If I say what's the inflection point, I know there's always this confusing concept of, okay, so is a point, is that the xy pair? I mean, yeah, that's what a point is on a graph. It's a coordinate, right? It's a pair of coordinates, or triple, or whatever, however many inputs you have. But when we talk about inflection point, traditionally we just list the x value. So as a point, so let me just kind of highlight that here. So when I say point, again, I'll just list the value of the input on the horizontal axis. Okay, an inflection point is a point on a graph for which the concavity differs on either side. So I'll say differs to, before I finish that, let's say I had this. Then there's going to be another inflection point over here. So I just want to make sure that when I say it differs on either side, it doesn't mean that everything over here is concave down and everything over here is concave up. I want to make it clear that it's just the immediate left and right. Okay, because there could be more concavity changes over there. So for which the concavity differs to the immediate left and right. Well, with the definition that we have, we really can only find that with a graph. But of course, the goal is to be able to find these types of points without referring to a graph and just using the function expression itself. So that's what I'm going to do, is I'm going to go ahead and take a look at a variety of examples, a variety of types of functions that have inflection points, perhaps some that don't, and just go through the procedure of how do we find those. For example, find any inflection points. I'm going to walk through, again, a variety of types of functions, and of course the main difference here is just the differentiation techniques for each type of a function. We'll find any inflection points. Part A, let's look at f of x is x to the third. And I'm going to go through part A in a little bit more detail than I will B, C, and D, again, just to kind of show you how the procedure fits together. Okay, so let's do the solution for part A. I'm not going to do this the most efficient way, but I want to kind of do this in more of sort of like a storytelling way, right? And then we'll get a more efficient procedure for the subsequent parts of this. F of x equals x to the third. That's a fairly simple graph to look at. So let's start by looking at the graph of this. F of x equals x to the third has the shape to it, where in the first quadrant it almost looks like some sort of a parabolic curve, but then it also has a piece in the third quadrant that's sort of a reflection of that. So there's f of x equals x to the third. And again, we can see over here, this would be concave up. Over here, this would be concave down. And that's to the immediate left and right of 0, which must mean that 0 is the inflection point. So according to the sketch, again, 0 is the point for which it's a concave down, concave up, so the concavity differs on either side of it. Well, let's sort of, again, use this as motivation. What do we know about concave down? We know concave down, I know that the second derivative is negative. Over here, concave up, I know that the second derivative is positive. Well, so what that tells me is that if I was to look at the graph of the second derivative, I just have to see where it changes from negative to positive or vice versa from positive to negative. So in other words, the sign changes on either side. If this is the graph of x to the third, let's also graph the function, the second derivative of that. So let's compare. All right, off to the side here, if f of x equals x to the third, then again, I want to graph the second derivative, so let's compute the first and the second. This is a power function, so the differentiation follows the power rule. X to the third would be 3x squared, and then to take the derivative of 3x squared, I would get 6x. So again, this is the second derivative of x to the third. Well, the graph of 6x, which we'll do down here, so again, this will be the graph. I'll do this in a different color here. I'll do it in the same color. All right, so then let's just kind of distinguish between these. Okay, this down here would be the graph of the second derivative. In other words, y is equal to 6x. All right, well, the graph of 6x is going to be a line through the origin with slope 6. So in other words, it's going to be a fairly steep line passing through the origin. And notice here we see that 6x is negative, and here we see that 6x is positive. Now, we didn't need to graph y equals 6x to figure out where it's positive and negative. We could just set this up as an inequality, which is what we're going to do in subsequent examples. But here's sort of the summary. If I want to find an inflection point, I have to determine where is it concave down, where is it concave up, and are there points to where it's different on either side of that. And this example illustrates what we're going to do is we're going to take the second derivative and we're going to solve this inequality. We're going to solve this inequality. So we're going to solve that pair of inequalities, and we're going to see if there's a point where the derivative has different signs to its immediate left and right. Okay, so that's going to be the overall procedure. Let's practice with that with another handful of types of functions. part B, I'm going to make a slight alteration to this. Again, we'll do it the more efficient way, and then we'll also kind of tie it back into the graph. But let's say I did the following. F of x is equal to, so I'm going to take a very similar function, and let's do x minus 2 cubed. Okay. As a reminder, what this all boiled down to was solving these inequalities at the bottom. The second derivative greater than 0, the second derivative less than 0. So let's go ahead and find the first and second derivative. The first derivative would be 3 times x minus 2, which is 3x minus 2 squared, which does not distribute. Like that. Okay, power rule, cubic, so that'll come down, and then the exponent drops by 1. So 3 times x minus 2 squared. Let's leave it like that, even though we could FOIL that. Let's leave it as is. Second derivative would be 6 times x minus 2. So there's the second derivative, and we need to find out where that's positive and negative. All right, so I'm going to set up the following inequalities. F double prime less than 0, f double prime greater than 0. Okay, second derivative is given by this expression, so therefore I have to solve the inequality. 6 times x minus 2 less than 0. Same expression, I want it to be greater than 0. This would be concave down. Solutions to this would be where the graph is concave down. Solutions to this are where the graph would be concave up. All right, both of these inequalities we can solve the same way. Divide by 6, add 2. Divide by 6, add 2. So what this tells me is that this function is concave down to the left of 2. It's concave up to the right of 2. Therefore, 2 is the unique number, well, unique in this case, it's not always unique, is the unique number for this function for which the concavity differs on either side. That tells me that x equal to 2 is the inflection point. X equal to 2 is the inflection point. Again, I emphasize the word "the" in this case, just to make it sound like there's only one. There could be many inflection points. Think of a trig function, like the sine function, where it just repeats over and over. There's going to be infinitely many. So there could be anywhere from no inflection points to a finite number to infinitely many, all sorts of cases. All right, let's verify that visually with the graph. The difference between the functions in part A and part B is I replaced x with x minus 2, and that means I've got a horizontal shift to the right by 2 units. So this graph would just shift over 2 units, giving me the following. And the point at the origin shifts over to 2, and there's my inflection point. Okay, so just kind of verifying with the graph. Let's take a look at another couple of examples, and then we will wrap up the video. Let's take a look at 2 types of functions. I'm going to do another cubic polynomial, but I'll have some written a slightly different way, and then let's do an exponential function. So part C, let's do f of x is equal to x to the third plus 3x squared. And then part D, let's do f of x is equal to e to the negative x squared. Okay. What I would suggest is maybe pause the video and try part C and D on your own using the technique that I illustrated in part B. Okay, so hopefully you had a chance to work through those, and let's see what you came up with. For part C, again, I need to find the second derivative. Therefore, let's compute the first derivative, giving me 3x squared plus 6x. And then the second derivative would be 6x plus 6. So I need to find out where this is positive, where this is negative. All right. The inequalities that I will set up would be where is 6x plus 6 less than 0, and where is 6x plus 6 greater than 0. So again, second derivative is negative, second derivative is positive. That tells me where the function's concave up, concave down, and then I can look and see if there's any points where it's different to the immediate left and right of those. All right. Subtract 6, I get 6x is less than negative 6, therefore x is less than negative 1. Over here, I get 6x is bigger than negative 6, therefore x is bigger than negative 1. And notice that to the immediate left of negative 1, it's concave down. To the immediate right of negative 1, it's concave up. Therefore, x equal to negative 1 typically my abbreviation, by the way, I think I used it over here too, IP for inflection point. So x equal to negative 1 in this case would be the only inflection point that cubic function has. Okay. Part D. So for part D, we need the second derivative, therefore let's compute the first. F prime of x. This is a composition of functions. I've got a quadratic plugged into an exponential. Composition, remember the differentiation rule is the chain rule. Chain rule, take the derivative of the function by ignoring the inside, giving me e to the negative x squared. Looks like I didn't draw my board off as well as I thought, so let me rewrite that. So the one downside with a whiteboard compared to a chalkboard is you have to make sure it's completely dry rather than erasing it. And erasing with the regular erasers on this whiteboard in particular doesn't clean it off very well. So usually I just have to use wet rags. Anyway, f prime is going to be e to the negative x squared, and then take the derivative of the inside, which is negative 2x. So I'll just rewrite that, negative 2x, e to the negative x squared. Okay, so there's an application of the chain rule. Now to take the second derivative, well, again, I've got this term here, so I do have another chain rule, but I've got a product now, so I have to use a product rule along with a chain rule. All right, product rule. Since this is a product of two functions, one of those factors, again, is going to require a chain rule. But the product, the derivative of the first factor is negative 2, so negative 2 e to the negative x squared plus the first factor times the derivative of the second, which is e to the negative x squared times negative 2x. All right, now let's clean that up. Now notice that this term and this term both have a factor of e to the negative x squared, so I'm going to factor that out. What else do they both have? Well, this has a 2, this has 2 and a 2, so it's got a 4, but it has a 2. So I'll actually factor out 2 e to the negative x squared. So what would be left over after we factor those out? From the first term, the only thing that would be left would be a -1. From the second term here, well, I did factor out a 2. I factored out e to the negative x squared. I've got a minus, which makes that a plus. And then I've also got x and an x, which makes that an x squared. Okay. So this is what I would get factoring the second derivative. Oh, you know what? I pulled out one factor of 2, so that means that there's, nope, my bad. If I had better editing skills, I would go back and delete the last couple of seconds, so sorry about that. For the second term here, I pulled 1, 2 out, but there was still 1, 2 that remained. Okay, my apologies. All right, now again, I need to find out where this is positive and where this is negative. Now, exponential terms, those are always positive, or at least they always share the same, whatever the sign of this constant is. If this was negative 2, then it'd always be negative. But this is never going to change signs, okay? What will change signs, or at least what potentially will change signs, would be this right here. Now, let's just quickly kind of verify that that will change signs. So this is going to be a quadratic function. The leading coefficient is positive, so it opens upwards. The y-intercept is -1, so that means it's a quadratic function. It opens upwards, and the vertex lies below the x-axis. So then it will hit the x-axis in 2 spots. Okay. Again, just to quickly, oops, as I throw my markers here, just to get a quick visual, that is a quadratic function, positive leading coefficient, so it opens upwards. Y-intercept is negative, so therefore it looks something like this. This is, again, part of the second derivative, right? Since this is positive, I could just call this the second derivative and say it's not really to scale. And therefore, we can see that it changes signs at the intercepts of this quadratic, okay? What I'm going to do then to find the inflection points is I'm going to solve -1 plus 2x squared is equal to 0. Notice this is not what we've done in the past. What we've done for previous examples is we would set the second derivative greater than 0, less than 0. What I'm going to do here is I'm going to set the second derivative equal to 0, because this second derivative we can see from the graph, since I've got that ability to look at the graph, I can see that the second derivative changes signs at the intercepts. Okay. Generally speaking, what I would do is I would set up the inequalities. All right, so this one right here, I can isolate the 2x squared term, so I'm going to get 2x squared is equal to 1. X squared is a half, so x would be plus or minus the square root of a half. And if you want to rationalize the denominator, that would be plus or minus root 2 over 2, and those would be your inflection points. All right, go back to the original function here. E to the negative x squared is the bell-shaped curve. Maybe some of you have seen this in a statistics class. When you, that vertex should have been, I'm going to cheat. The vertex of that should have been on the y-axis. So sorry about that. Of course, now it looks like a crooked y-axis. Whatever, you get the point. The idea is that this is the bell-shaped curve related to the standard normal distribution that you see in your stats course. Anyway, so I'll go ahead and wrap up the video here. This is how you find inflection points for functions.